This video is going to be on percent composition, hydrated compounds, and empirical molecular formulas. So it's in your notes. It's numbers 19 through 24. I'm going to do a few examples of each one of those. So number 19 is talking about percent composition of a compound. If we have a compound like water, you might say that the percent composition, you might say that it's 2/3 hydrogen, 1/3 oxygen. That would be true in terms of number of atoms. 2 out of 3 atoms are hydrogen, 1 out of 3 is oxygen. But when I say percent composition, I want to know in terms of mass. So if you're drinking a container of water, most of the atoms you drink are hydrogen. There'd be double the hydrogens as compared to oxygens. But most of the mass comes from oxygen because oxygen has more protons, neutrons, electrons. It weighs 16 grams per mole, whereas hydrogen is only 2 grams for the 2 hydrogens. So when I say the percent, I want to know the percent in terms of mass. So number 19 in your packet wants to know if we have barium sulfate, what the percent is of each element in barium sulfate. So to do that, to find the percent of barium in the compound, I would take barium's mass, which is 137 grams per mole. Sulfur is 32 grams per mole. Oxygen is 16 times 4, which is 64. That total mass for those three is 233 grams per mole. So if I want to know the percent of barium, I'm going to take barium's mass, which is 137, divided by the total, which is 233. Okay, and then turn it into a percent. So make sure you move your decimal over twice. So that percent is about 58.8%. That's the percent of barium. If I want to do sulfur's percent, I would take its 32 grams divided by the total again. So we're trying to find the part out of the whole, and that's about 13.7%. So I could add those two and take 100 away from it, or take 100 minus those two to get oxygen's percent. Or since oxygen is double sulfur, I could just double that percent. Oxygen would be about 27.5%. So if I want to find the percent of each element in a compound, we're not talking about numbers of atoms, talking about the mass of them. Number 20 in your notes is talking about hydrated compounds. Okay, so this is number 20 in your notes. It's talking about hydrates. Okay, and hydrates are compounds that have some water attached to them. So I've got one here, magnesium sulfate heptahydrate. That's the example that's in your notes. So it's magnesium sulfate hepta, which means 7, hydrate. Magnesium sulfate heptahydrate. So what that means is for every molecule of magnesium sulfate, there's 7 water molecules attached. Doesn't mean that it's wet, okay? Those are water molecules you cannot see, but there are water molecules in here. So when I buy this container, a lot of the mass of it is actually water. We'll use this compound in the lab, or compounds like this in the lab, and I'll kind of show you what those are. But for right now, I just want to know what is the percent of water in that compound. Percent of water in that compound. So again, I'm going to add up all this. This is not a multiplication sign right here. It just means you have this compound plus 7 waters. So this is about 24 grams. That's 32 grams, and that's 64. And then we have 7 waters. So I'm going to take 7 times 16 plus 2 is 18, so 7 times 18. And that total is 126. So I'm going to add up 126, 64, 32, and 24 for the total. So if I want to know my percent of water, I'm going to take water's mass, which is 126, divided by the total of all those. And that total for this one is 246 grams. So out of the 246 grams, 126 of them are water. That percent is about 51.2% water. So when I buy this chemical, 50% of the mass of what I'm buying is actually water molecules. Okay. That makes the compound a little bit more stable, though. There's some reasons for that we'll get into in class. So again, those are hydrates. The last part of this is going to be the empirical and molecular formulas. Okay, empirical molecular formulas. And first thing, the difference between an empirical and molecular formula is this. So this is glucose, C6H12O6. That is a molecular formula. That is the actual formula for glucose. It's a molecular formula. The empirical formula of glucose would be this reduced. So empirical just means what is the simplest ratio of the elements? Well, these are in a 1 to 2 to 1 ratio. There's twice as many hydrogens as there are those. So the empirical formula is CH2O. That is the empirical. It's the most reduced form. Now, for some compounds, the empirical and molecular would be the same thing. For example, water. That is the actual formula for water. That's the molecular. It's also the empirical. It's the most reduced form of the compound. So when we try to figure out formulas of compounds in labs, we always end up with the most reduced form. We may have to figure out another way to figure out the molecular form. I'm going to do two problems in your notes, number 23 and 24. Okay, so 23 is saying, what is the empirical formula of a substance made of phosphorus, a substance made of potassium, manganese, and oxygen. So and it tells you it's the compound, so the compound has K, Mn, and O in it. So what I want to know is what is the formula of that compound? So how many potassiums, how many manganese, how many oxygens? Remember, this ratio is in terms of atoms or moles of atoms. It is not in grams. So I need to get these into moles. So it tells us that it is 24.7% potassium. Well, I'm just going to pretend like we have 100 grams of this compound. I could choose any amount, but 100 is easy. So if I said we had 100 grams of that compound, that means 24.7 of those grams would be potassium. 34.76 of those grams would be manganese, and 40.5 of those grams would be oxygen. We're going to turn those into moles. So divided by the molar mass of potassium, that's 39 grams for every mole. So I do that, I get 0.633. Do the same thing for manganese, that is 55 grams for a mole, 0.633. And for oxygen, it is 16 grams for a mole. That is 3.52. So again, this is moles of potassium, this is moles of manganese, and this is moles of oxygen. I can't write the formula like that, though. I can't write K 0.633, Mn 0.633, O 2.53. I'm sorry, not 3.52, 2.53. So I need to figure out what the ratio is of these. Well, obviously, these are in a 1-to-1 ratio, so that's probably going to be 1 and 1. I need to figure out how many times bigger this is than this. Easiest way for these is always divide by the smallest amount. So if I divide this by 0.633, divide this by 0.633, divide this by 0.633, it tells me I have 1 to 1 to 4 ratio. It's a 1 to 1 to 4 ratio. I would make sure when you're finding your moles, you leave several decimal places. These may come out to like 0.99 or 4.01, but pretty close to a whole number ratio from there. So for every 1 potassium, there's 1 manganese, there's 4 oxygen. So my formula becomes K1, Mn1, O4, KMnO4. Now that is the empirical, the most reduced form, but it's actually the molecular in this case. But you're always finding the empirical here in this. One more example there. I'll do number 24. So 24 is saying you have an acid called succinic acid. Okay, same type of thing. It's telling us we have 40.68 grams of carbon. So I'm just going to turn those into moles. So the compound has carbon, hydrogen, oxygen. So we have 40.68 grams of carbon divided by 12 grams is a mole. We have 5.08 grams of hydrogen, which just means that I have 5.08 moles because every gram of hydrogen is a mole. So hydrogens are always easy to do. And 54.24 grams of oxygen. 16 grams is a mole. So that gives me 3.39 moles and 3.39 moles. Again, once we get that, we find the simplest ratio of them. So I'm going to divide them all by the smallest amount, okay, which in this case is 3.39. So divide this by 3.39 gives me 1. Divide this by 3.39 gives me 1.5. Divide this by 3.39 gives me 1. So we know we have a 1 to 1.5 to 1 ratio. So if I write my formula based on that, I can write C1 H1.5 O1. Still, it needs to be whole numbers. Okay, an easy way to get those in whole numbers would be to double each of them. So I can double this, make it 2, double that and make it 3, double that and make it 2. So this ratio here was a 2 to 3 ratio. So we end up with C2 H3 O2. That is our empirical formula. That is our most reduced formula, most reduced form of the compound. It also asks us to get the molecular formula in this case. Okay, so this is the empirical formula. It tells us that the molar mass of this compound is 118 grams. So the real compound has to weigh 118 grams. If I add all these up, so 2 carbons is 24, plus 3 is 27, plus 32, that ends up being 59 grams for that. So remember, the molecular formula will always be a multiple of this. Either this doubled, this tripled, this quadrupled. 59 goes into 118. So take 118 divided by 59, goes in 2 times. That means I need to double this to C4 H6 O4. That is my molecular formula. So this is the actual formula of the compound. That's the most reduced form of it.